Welcome to the ET380 lecture video on oscillators, voltage controlled oscillators, and phase lock loops. Here's a diagram of a damped oscillation where the oscillation reduces and shuts off. Okay, here's an undamped oscillation where the oscillation continues, and this is what we want to use in an oscillator. There's two types of oscillators. One is a sinusoidal oscillator, and between 20 hertz and 1 gigahertz, and non-sinusoidal oscillators where square, rectangular, or sawtooth waveforms, and they go between 0 and 20 megahertz. Here's a block diagram of different types of oscillators. We have tuned oscillators, which include RC, which are resistor capacitor, LC, inductor capacitor, and crystal oscillators, where we use piezoelectric crystals, and two different types depending on the manufacturing technique. Then untuned oscillators, relaxation, and ring oscillators. A tuned oscillator includes inductors and capacitors. They're used to generate high-frequency signals, also known as RF oscillators, and they include Hartley, Colpitts, and Clap oscillators. RC oscillators use resistors and capacitors, and they use it to generate low-frequency or audio frequency signals. Phase shift and wine bridge oscillators are included in the RC. Crystal oscillators are used to generate highly stabilized output signal. They're good for up to 10 megahertz. Negative resistance oscillators are used for very high frequencies, and they use tunnel devices and other type devices. Here's an oscillator using a tank circuit, which is an inductor and capacitor, and they resonate at their resonant frequency depending on the impedance of both devices. They need to be amplified, and they need a feedback network. And the amplifier, so the gain of this device has to be more than 1 in order to oscillate. Okay, here's an animation of an LC circuit, resonant tank circuit. The capacitor will charge and then discharge into the inductor. The inductor will make the magnetic field, and since these two are at the same resonant frequency, they will continue to oscillate between these two devices, and that's what gets us our frequency based on their resonant frequency. Okay, here's a Hartley oscillator, and it uses a transistor amplifier. It also may use an op-amp. And here we have our tank circuit, and this one uses inductive feedback. 2 inductors and an adjustable capacitor. So this is a Hartley oscillator. Here's a Colpitts oscillator, and it uses capacitive feedback from our tank circuit, and it'll output a sine wave. Again, we have a transistor amplifier. This circuit requires a gain of greater than 1, and again, it could also use an op-amp. Here's a Clap oscillator, and it uses capacitive feedback, and it's a version of the Colpitts oscillator. And here we have capacitive feedback, and we've added an inductor in the output circuit. Okay, here we have our crystal oscillators, and what happens is we put a voltage on a thin piece of crystal, and it changes shape. And this is called the piezoelectric effect. And when it changes shape, it produces electrical charge. And this electrical charge will resonate at the frequency that the crystal was designed for. Here's a diagram of a crystal oscillator that's resonant, and it's going between capacitive and inductive. And this is based on its resonant frequency. And here we're showing the series resonance and parallel resonance, and it at its resonant frequency. Here's a schematic symbol for a quartz crystal with the metal electrodes, And the equivalent of circuit would be a LC, RLC actually, and with a parallel capacitance based on the metal plates. Here's a crystal oscillator. It's a Pierce crystal oscillator with the crystal setting the frequency. And this is a junction FET. And there's a circuit for the Pierce crystal oscillator. Here's a Colpitts crystal oscillator. Here's a crystal setting the frequency and using an NPN transistor as the amplifier. And this one frequency would be based on the crystal. Here's a crystal oscillator circuit used for the clock of a microprocessor or a microcontroller, and it's added a couple capacitors. Here's a VCO or a voltage controlled oscillator. These are used quite a bit, and we put in an input voltage and it'll control the frequency depending on the design, either a sine wave, rectangular wave, triangular wave, or a saw wave output. So they come in all kinds of different devices. Here's a phase lock loop where we put a frequency in, a signal, and we will have these different devices will maintain that frequency on the output even though the input may change. So we have a reference frequency, a phase detector, a voltage controlled oscillator, and we'll get an RF signal out, and we'll have an error voltage from our phase detector filtered back into our loop filter, and this error voltage will go back into our VCO and maintain our signal. This is a simplified phase lock loop diagram based on the FCC test where we have a reference frequency, phase detector, active low pass filter, which I also call anti-alias, and a voltage controlled oscillator and an output signal. Here's a phase lock loop IC. This is the LM765, and it's an obsolete device but still available. It's used for data and tape synchronization, modems, FSK demodulation, FM demodulation, frequency synthesizers, tone decoding, frequency multiplication and division, SCA demodulators, telemetry receivers, signal regeneration, and coherent demodulators. Here it's showing a multiplier, frequency multiplier by 10, where we use a 7490 divided by 10 device, and it ends up multiplying the input frequency by 10. Here we have 10 kilohertz in and 100 kilohertz out. Here we have digital frequency synthesis. So we have direct digital synthesis is where we have a memory device which contains all the sine functions stored, and then they're called and refed to a digital to analog converter where we end up with a sine wave based on that information. And we have a direct frequency synthesis. Back in the old days, they'd actually use a crystal for each frequency. No longer used, I believe. Okay, here's a direct digital synthesis block diagram. We have our clock, and we have a numeric controlled oscillator, which includes a phase accumulator and a ROM lookup table, which has our sine wave information, goes out to a digital to analog converter, and then goes out to a low pass filter, anti-alias filter, and then we get our frequency out. Okay, variable frequency oscillator, an analog where we use either a inductor, adjustable inductor, or adjustable capacitor, and we could get the frequency out. We could use a tuning capacitor, and we could change that with the capacitance, and the old capacitances were the metal plates, and they could change the frequency. And modern radios, the term VFO is often used, but modern radios use digital frequency synthesis for oscillators. Here's a picture of one used for ham, and it is an obsolete device. Here's a negative resistance microwave oscillator. And it consists of a gun diode. Here's a picture of a gun diode, which is a negative resistance device. There is the curve, and it's put inside of a cavity, which radiate out the aperture into the waveguide. And there is the device there, and the waveguide. And this is used for microwave oscillators. These are probably obsolete devices since they're both Russian.